Welcome back. Last time we were looking at ways to speed up the convergence of the inverse tangent series expansion. That involved using this trig identity. I've repeated it here for convenient reference. Today we are going to explore another way to verify such identities. It will involve a detour using complex numbers. If you've never seen this before, don't worry. Just as every real number can be represented on a number line, every complex number can be plotted on a complex plane. The x-axis represents the real component, and the y-axis represents the imaginary component. In this case, 2 plus I, we move over 2 units and up 1 unit. This vector can be thought of as a triangle. By definition, tangent theta is equal to opposite over adjacent. Using my labels a and b, tangent theta equals b over a. So what if I want to multiply two complex numbers together? a1 plus b1i times a2 plus b2i. To do that, I'll need to FOIL out and collect like terms. That's what I've done here. Remember that I times I, or I squared, is equal to -1. Collecting like terms leaves me with another complex number that can be plotted as a vector in the complex plane. The tangent of that angle, theta, can be expressed as a ratio of the imaginary component over the real component. That is seen boxed in orange. Now wait a minute. That looks very similar to the result from the last lesson. Putting 2 and 2 together, we conclude that the sum of two inverse tangents is equal to the product of two complex numbers. Now you may be wondering why this is important. In a moment, we will see an example that will hopefully shed some light on that. Before we move on, just note the expression in the last line. Take n equals 2, for example. If I add inverse tangent to itself, that's the same as multiplying a complex number by itself. A plus bi quantity squared. The same idea applies to any number n in general. This will help us out very soon. Remember this guy? We showed why it is true using the trig identity for tangent. Now let's verify the same thing using complex numbers. 1/2 becomes 2 plus I, and 1/3 becomes 3 plus I. FOIL those out. Collect like terms. Express as a ratio of the imaginary component over the real component. Inverse tangent of 5 over 5. That's the same as inverse tangent of 1, which we know from geometry is equal to pi over 4. Indeed, that is identical to what we found before. This is just another way of getting there. Soon enough, we will see that this approach greatly simplifies things. Here's another example to drive home the point. 1/5 becomes 5 plus I. The coefficient 4 becomes a power. 1 over 239 becomes 239 minus I. Why minus? Because of the negative sign preceding the inverse tangent. Same thing as before. Expand 5 plus I to the 4th. Collect like terms. FOIL that with 239 minus I, and collect like terms again. When expanding 5 plus I, don't forget the binomial coefficients underlined in red. Where do those come from? In case you needed a reminder, we can get those from Pascal's triangle. Each number along the left and right side is 1. Every number in the middle is the sum of the two numbers above it. So, for example, 6 is equal to 3 plus 3, as seen in blue. Likewise, 15 is equal to 10 plus 5, as seen in green. This pattern can continue as long as you want it to. For a binomial raised to the 4th power, we pull coefficients from the 5th row down. 1, 4, 6, 4, 1. Indeed, those are the numbers we use to expand 5 plus I to the 4th power. Now back to the example. After we've expanded and simplified, we have another complex number. This can be represented as a vector in the complex plane. The angle theta is the inverse tangent of the ratio of the imaginary component over the real component. In this case, 114,244 over itself. Inverse tangent of 1 is equal to pi over 4. Boxed in orange, we reach the same conclusion using complex numbers that we did using trig identities. Thus far, we have only seen the sum of two terms. It turns out we can speed up convergence even more by using three terms. This is just one example. Before we do any computations with it, let's verify that this is in fact a valid expression equal to pi over 4. To do that, I first shuffle over one of the terms to the right-hand side and rewrite pi over 4 as inverse tangent of 1. Then I express these as complex numbers. What's next? In order to prove that this is a valid expression, I simply have to show that the left-hand side is equal to the right-hand side. The numbers we are going to see become quite unwieldy. In fact, they are so large that most handheld calculators cannot display all the digits. For the first go-around, we are going to power through with brute force in spite of that. First, the left-hand side. I have omitted the details, but you can verify these numbers for yourself if you so desire. 18 plus I to the 12th power is quite large. So is 57 plus I to the 8th power. Their product is even larger. 29 digits for each component. Yikes! Next, we take the ratio of the imaginary part over the real part. Believe it or not, those numbers simplify as seen boxed in orange. The right-hand side isn't quite as bad, but it still gets cumbersome. 239 minus I to the 5th power. Foil that with 1 plus I. Take the ratio of the imaginary part over the real part. Amazingly, that simplifies to the same ratio we just saw on the last page. Conceptually, this idea is simple enough. Unfortunately, the actual arithmetic gets so out of hand that I fear it may cloud the clearer truth behind it. That's why next time we are going to try again with a modified approach to make the arithmetic more manageable. The takeaway for today is that we can verify expressions to find pi by using the product of complex numbers instead of tangent identities. This alternative approach can greatly simplify things. Feel free to post any questions you may have in the comments section below. Otherwise, thank you for watching. I look forward to seeing you again.